Good morning. I'm Jonathan Chu. I'm a software developer here at the Software Engineering Institute. It's my pleasure to present an overview of two of our projects. Why did the robot do that? And what will the robot do next? In order to get a broader adoption of autonomy, we first must trust it. And here at the SEI, we're looking at ways to improve that trust. And trust ultimately begins with understanding. For a moment, I'd like everyone to kind of picture in their mind what the state of the art of a robotic system looks like. Some of you guys may have pictured like maybe an industrial arm, something you see in a factory. You might see, you've been in Pittsburgh, you might see these self-driving cars that are driving around town. Others may see the humanoid type robot that you might see here on the screen. And while all of these are kind of state of the art, they all look a little bit different. But one thing that's present in all of these scenarios that we think about are, I'll call them large-scale safety systems, right? Chimp, you have a tether here. On your industrial arm, you have lockouts, you have e-stops, you have hard stops. The Uber driver, you have a physical driver there. And what is that telling us about our confidence in these systems? We don't trust them, right? We have to put this here and in place because the system is not behaving the way we expect. It's not understanding us, or we're not understanding it. And so what do we have to do? I argue that we have to do what we do with people. We communicate. We have to communicate with these systems. We need the systems to communicate to us what their intent are. We need this to communicate to the system what our intent is so that we can work together. So we need the robots to convey their sense of, and sense those intents and infer them. And these systems aren't designed for that. We're designing robotic systems to be optimal performance, right? It's going to do its task. It's going to do it well. It's going to do it right within some subset. Bobby was talking about, the engineering constraints. We're trading things off, right? One of the things we've traded off many times is us, this gray matter, and how we interact with them. So how do we do all of this together so that we can build trust? So over the course of this project, or these projects, we took a bunch of different approaches. So it's kind of a breadth approach to this. We looked at how maybe the robot could proactively change its behavior so that we could infer what's going on. And this could be simply, hey, let's turn on a turn signal. This could be turn on a light. It could be displaying maps. It could be other verbal and nonverbal explanations. Excuse me. And the other thing we looked at is how do we team that? How can we improve mission performance? Because ultimately why we design these systems is to create and solve a broader problem. So how can we work together with them to solve that problem? And so we use technology like gaze tracking glasses. We produced different visual and non-visual methods for this, and then also a teamed interface. So I'm going to walk through a couple different examples, kind of high-level overview of what we've done. So the first approach, I'm going to talk about this concept, is neglect tolerance. The idea here is how you trust a system, potentially, can be measured about how much time you spend ignoring it. Let's go back to that again. How much time you spend ignoring it. Because if you're paying attention to it, you don't trust it. If I don't trust it, I have to watch it. I'm trying to do a task. But however, if it goes off and does it on its own, and you don't pay attention, you don't check in, it's doing pretty well. You can see this in levels of autonomy as defined for self-driving cars, right? Level 0 is here, I'm sitting there driving. And level 5 is, I don't need to intervene at all. I don't need to be paying attention. And there's something in between, which is, well, like adaptive cruise control. It's going, but I have to steer the wheel. But if something comes up, maybe I have to hit the brakes or something like that. And so these are different tiers of attention that you have to pay to the system in order to see what level of autonomy you're at. And what we were looking at was, can we use gaze tracking glasses to measure where you're looking as an operator and compare that against how the system's operating and see if you're spending too much time looking at it, maybe it's not doing that. Then on top of that, as a baseline, can we look at having the robot act in a way that conveys its intent? Again, back to the signals. That's an easy one, right? You turn on your left turn signal, you assume it's going to turn left. If it leaves it on too long, maybe you're in the wrong area and it's going to do the eventual left where it still turns right. But how do we get it to convey that information and in a way that you can understand? Or alternatively, how can it do something to get your attention? Maybe it needs to get your attention because it's going to violate your expectations soon. So the goal here was to look at how do we look at the system as a human, convey that information of where we're looking so that both the robot can interact with and react to that, or alternatively, how could we measure inattention, if you will. The second approach here is actually resulted in an accepted paper to this year's ROMAN 2017 conference, a conference on robot and human interaction. In this work, we looked at how a robot could generate paths to indicate preference. And so this is an example of us using those nonverbal explanations to indicate its preference. And so what you're seeing on the right, yeah, that's my right, hand side is a bunch of different graphs that it's generating. A key here to remember is that it's generating them. It's trying to show you in the terrain that it simulates and the path that it chooses what its cost function is. Instead of having you to observe it from some non-trivial amount of observations and pick different terrains, it says, no, let's flip that around. I can generate the terrain, I can generate the path, put those together, can you infer what's going on? And then, again, back to one of the earlier premises that I had, robots aren't built to convey this intent. So we're trying to press really hard on this so that we can understand what's going on. We wanted to look at how much information is necessary so that you could understand or gain some understanding without confusing you. Because if I just gave you this with no context, you'd say, okay, John, you did a great job. You drew some dots. There's some green. There's some red. Okay. But what we have here is different types of data points. You'll see in the red where it's changing direction, or you see in the yellow where it's what we're calling compromise points, where it's going over in areas in which it would not necessarily want to go over, except it's the optimal solution. And so when you use that information, you build in your head a model of what the robot or the system is trying to do based on these different types of points. And so these changes, these lacks of changes, are indicating to you the robot's preference. And we measured this and compared this against what the human thought the robot would do. They drew paths. And we saw that depending on how much information you gave, you gained some knowledge about what the system was going to do. And you could convey a sense of the robot's preference with some limitations. The last approach that I kind of wanted to show was a collaboration with Josh Peschel over at Senformatics. And here we're looking at human-robot teaming for unmanned surface vehicles. And to give you some context, here's some of the platform's capabilities, as well as a clip of it operating and driving around, driving. So here, it can operate in a lot of different terrain, and we wanted to see with the interface, which you'll see in a second, kind of how we can team the robot with this extra information, these other explanations, so that we can get better performance. Because ultimately, it's about, again, the mission performance. We care how the system's going to work. We care how people solve the task. And so we created this interface that for basic use, we're driving boats around a river or a small stream, and we're trying to do a search task. And so the robot users have different ways to look at it. You can drive it around. You can save points for later so that you understand what's going on. And we wanted to measure how this goes against without the additional explanations versus with the additional explanations. So, okay, come on, video. And so we have this just generic user interface. What we're about to see is an explanation. This is a verbal explanation. This is the system telling the user what it did and how it went about doing it. Right? I traveled north and to the west and along this river, this distance. And so now it's trying to tell you what it did. And the hope here is while you're operating, if it did an autonomous action, you understand it better than rather than get the blue track just on its own. You have a sense of why it turned, what it was trying to do. And so now when you go in and to do maybe follow-up investigations or try to do things on your own, you believe in the system. You trust it more. And initial studies, or initial results of the study said that the mission performance went up. We were able to find things better. We were able to find things a little bit quicker, and they felt more confident that the robot was doing what it said it was doing based on the visual path that was given, the verbal explanation, and among other things. And so we used this surface vehicles and coupled with prior research about UASs to show that this improves overall mission performance. So we wanted to couple that together to say, hey, look, we can do a better job. I think that's it. Okay. So over the course of these projects, we looked at different approaches for explaining robot behavior. We looked at verbal and nonverbal explanations and approaches so that we could understand it. We also looked at how can a robot adapt its behavior to improve the human's performance and kind of increase that measure of neglect. How can we ignore it more, if you will? And then we looked at how do we combine it all together to say, hey, again, we're about our mission. We're not just about playing with robots while it's awesome and it's fun. We care about the mission, right? And so how do we combine it together? And we intend to continue fleshing out these forms of explanations and approaches to improve the trust in autonomous systems. So looking forward beyond this, what we're trying to do is we're trying to build off of some of these ROS-M efforts that we have with TARDEC and to demonstrate these on more mature systems so we can say, okay, we did this in a lab in its own space. How do we build this on top of existing robotic frameworks and architectures? How can we look at more mission challenges, direct mission challenges, or operational constraints? How might these affect the ability to explain or not explain these environments? And then also diversify beyond just the robotic planning applications and stuff like that. This work can be extended to other autonomous systems like AI, machine learning, and ultimately for the kind of third offset strategy that Jeff mentioned is we need to understand what it's doing. I mean, even Scott was talking about it a little bit, understanding what are the steps and expressing it in human understandable math and not just math. And then I want to conclude with this. If you only remember one thing about what I said today or about this presentation, it's just that we here at the SEI are working really hard to develop trust in and understanding of robotic and autonomous systems so that we can increase their adoption and ultimately increase the force multiplying effects that we expect them to have. That's it. Questions? Oh, the best part. Sorry.
Jonathan, thank you. Great presentation. Excellent work, obviously, from CMU and SEI. Every time I'm a double E in computer science, and I always, whenever I think about robots, I think about like multiple things in my brains beside the physical, mechanical aspect, artificial intelligence. I worry about that because that, if in the wrong hands, it could be programmed differently. Cybersecurity, if somebody hacks into the system. And the third thing is GPS and radar and LiDAR. So from your perspective, I know it is a little bit different, but what are your thoughts, like from an SEI perspective, about safety and security as more and more robots are entering the industry? Thank you.
Okay. I'll talk about it in kind of a couple different ways. One, I'll highlight some of the work we're doing with TARDEC on the ROS-M. One of the big components there is assurance and building tools and developing tools to assure that the code is written properly, both from a cyber perspective, from an operational perspective, and a functional perspective. VMV is hard on these systems. From a formal models perspective, I know there's research being done at other groups in the SEI that are looking at formally describing these autonomous systems or these cyber-physical systems so that we can produce a high-level description, formally check it, and go from there. And the last one was GPS denied. And so there's other techniques when you're looking at SLAM, simultaneous location and mapping, and other means to do that that are being used. And you can look at like the Ubers and stuff like that and that are doing self-driving. While they use GPS as a strong one, they're almost creating rails for themselves. How well-defined the maps are, how well-defined the information they have, I believe they could effectively go with GPS without GPS because of how good their mapping is being done right now. But that's all done a priori, and in the context of the department, that may not be the case. There are probably other solutions for PNT that can aid in that